Okay, so my name's Shri, and I'm a postdoc working with Andrew Bagley and Nick Parker in Newcastle University, and today I'll be talking about some very preliminary results that we have on vortex interactions and dipolar superfluids. But first, I'd like to thank the organizers for organizing this wonderful workshop, and especially Illuminita for accommodating my request to give a talk at the very last minute. So, so today Veju Bao gave a really nice talk about dipolar BCs, so I won't have to talk too much about why we might be interested in dipolar interactions and superfluids. But the one thing to note is that not all Bose-Einstein condensates have interactions that can be approximated as contact. For instance, magnetic species such as chromium, erbium, dysprosium, etc. have large intrinsic magnetic dipole moments, and these magnetic dipole moments cause the superfluid to not only have these short-range interactions, but also long-ranged anisotropic dipole-dipole interactions. And then the interplay between the short-ranged and the long-ranged anisotropic dipole interactions cause some interesting effects that don't occur in conventional atomic superfluids, such as a rotonic spectrum, the supersolid phase, where you have both long-ranged order and short-ranged crystalline order coexisting, and as I'll talk about today, some modified vortex-vortex interactions and dynamics. So, originally in 1995, when BCs were produced in the lab, these were from alkaline species such as rubidium or potassium, and they have a very small magnetic dipole moment. But from 2005 onwards, with the production of BCs of chromium, dysprosium, erbium, and so on, the dipolar interaction strength from the magnetic dipole moments is large enough, at least well over an order of magnitude compared to the old alkaline BCs, that you have to consider the magnetic dipole moment, magnetic dipole interaction in addition to the van der Waals interaction. So we're all familiar with magnets. If you have two magnets with a north and a south pole, you have repulsion when the north poles are close to each other, but when the north pole and the south poles are aligned, you have attraction. So that's encapsulated in the cosine theta dependent term in the dipolar interaction. It's also long-ranged. There's a 1 over r cubed dependence of the interaction. And the free parameter, when we dimensionalize it properly, is this parameter here called epsilon dd. So one thing that happens in superfluids, which I urge you to keep in mind throughout the talk, is that just like your classical magnetic system, the dipole moments energetically align preferentially parallel to the magnetic field. So you have these two magnets would like to align such that they're like so. Now, how do we account for the dipolar interaction in the Gross-Berezovsky theory? We have to include this additional dipolar term, which is a convolution of the density and the dipole-dipole interaction, where I remind you that's what that is. And unlike Veju, who solved the dipolar Gross-Berezovsky equation by using the delta function trick, I'll be solving it throughout by treating it in K-space, so the interaction's given there. And one of the interesting things about dipolar BCs is because the Bogoliubov spectrum is anisotropic in K, you have a situation where, hopefully you can see it over here at the bottom, you have a situation where for large enough values of epsilon dd, you get a mean field collapse of the system as the dipoles align like so, and then collapse. So you can only have mean field stability when the parameter epsilon dd is between minus 0.5 and 1. But I'll only consider values between 0 and 1 in this talk. Now, just some interesting phenomena that occur in dipolar BCs. I'll skip the supersolidity, but I'll instead focus on the fact that it there's never been a better time to discuss, to investigate vortices in dipolar BCs, because last year in the Faleno group in Innsbruck, they produced vortices for the very first time in dipolar superfluids, in dipolar BCs, by basically taking a harmonically trapped dipolar BC and rotating the applied magnetic field so that from a previously vorticity-free gas, the dynamical instability of surface waves caused vortices to enter from the edges. So things like this have been done in scalar BCs by rotating the harmonic trap. They were able to do this simply by having a time-independent trap, but by rotating the applied field to create vorticity. I did mention rotons in the very first slide, but I'll have to talk about that a little bit more, because in a dipolar BC, you can think about the existence of rotons as being due to basically a localized depletion of superfluid. Actually, I'll skip to the next slide so that I can understand, so that I can explain what's going on. Consider a depletion of superfluid in this zone over here in the middle. You have superfluid on the left and the right, so the dipole moments are pointing up, parallel to the magnetic field. But in analogous to the condensed matter system, where in a positively charged gas of charges, you can consider vacancies of the charge as being negatively charged, holes. You have so-called antidipoles, which are pointed downwards. And so it doesn't really matter if the magnetic field is parallel to the depletion zone, because if you consider the magnetic dipole interaction between the antidipole in the center and then the dipole moments around it, they all cancel out. So there's no screening of the magnetic dipole interaction. But in case 2, where you've got, where we're now looking top down, and you've got a magnetic field pointing to the right, in the bulk, in the exterior, you've got magnetic dipoles pointing to the right. But you've got a virtual antidipole pointing to the left, where there's no superfluid. And if you consider this, the interaction between these dipoles, between the real dipole and the virtual dipole, is attractive here, but is repulsive over here. So all things being equal, you should get an accumulation of superfluid here and here, and a relative lack of superfluid here and here. So this is the reason why in dipolar superfluids, when you have strong confinement in the quasi-2D system, as Weishu discussed, you can have a rotonic energy spectrum in certain cases. So as you increase, on the left, as you increase the dipolar interaction strength, you get the classic rotonic spectrum that gradually becomes unstable as you increase the dipolar interaction strength further. And this can be measured in experiments by looking at the dynamical structure factor. Now, let's talk briefly about vortices. I'll bring up a figure from a paper that Weishu discussed, also co-written by Yongyong Tsai at this conference. An interesting feature of vortex lattices in dipolar BECs is that, unlike in the vanilla case, you not only can have the possibility of having triangular vortex lattices, but as you change the angle made by the magnetic field with respect to the vortex axis, you could also get square vortex lattices, and you also can have some interesting striping phases between the vortex arrays. And this is basically due to magnetostriction. If you have an absence of charge, absence of magnetic dipoles where the vortices are, it creates channels where the energetically preferable alignment of the magnetic dipoles is for them to be polarized along those channels. And also in some old papers in harmonically trapped systems, you'll notice that the density field of the condensate is peaked on these sides, and there's a trough on the other two sides, in contrast to a non-dipolar BC, where the density profile around a vortex would be isotropic. Now, these two features of vortices in these harmonic systems made us think, why don't we get rid of the trap and just consider a uniform system and see if these features are due to the trapping or if they're an intrinsic effect of the dipolar interaction in the absence of trapping, in the absence of any other vortices. So we can do the Madelung transformation, and what we'll do is we'll consider vortices that are polarized along the z-axis, but with the magnetic dipoles polarized along the x-axis. And because the Gross-Bertayevsky equation features compressibility, what it means is that if you get an anisotropic density profile, you must also have an anisotropic velocity field and also an anisotropic phase field. So what we do is we don't just imprint the vortex phase and in imaginary time just allow the density to evolve. We have to allow the phase to evolve independently of the density profile. So we impose the Neumann boundary conditions so that we can have a single vortex in the grid. And we imprint a vortex initially at the center of the grid, and we try to find ground states via the method of steepest descent. So what do we have here? We have 3 different rows where the dipolar interaction strength ratio is 0.3, 0.6, 0.9. So more and more dipolar. And on the left, we have the difference between the density and the angular average of the density. In the middle, we have the difference between the phase and the angular average of the phase. And on the right, we have the expectation value of the dipolar potential. So I'll first point out the correlation between the density and the dipolar potential. Wherever you have a peak of the dipolar interaction, you see a corresponding trough in the density. And on the other hand, wherever you have a trough of the dipolar potential, you see a peak of the difference between the angular average and the real density. So this is basically akin to the rotonic density fluctuation that I talked about, where you'd see a higher dipolar interaction potential over here and a lower dipolar interaction potential over here. And you'll also see that compared to the non-dipolar incompressible phase, due to the anisotropy of the density, you also see lobes of compressibility of the vortex phase around the vortex core. So how does all of this affect simple vortex-vortex dynamics? We'll look at 2 basic cases, a like-signed pair and an opposite-signed pair. So I'll first talk about the same-signed pair. In point vortex dynamics, or savoir without any curvature of the vortex lines, we expect the trajectories of a vortex-vortex pair to be circular, and then the velocities of the 2 vortices to be dependent on the separation of the 2, separation between the 2. But as you can see, as we increase the strength of the dipolar interaction, we don't see circular trajectories. Instead, you see small dipolar interaction strengths. You see a semi-major axis along y and a semi-minor along x. And as you ramp up the dipolar interaction to strengths very high, you actually see a more dumbbell or Cassini oval-like shape. And we attribute this to an interplay between the vortex-vortex interaction due to the dipolar interaction, and then the usual kinetic energy from the vortices. So here, the interaction strength is higher than here, so you can increase the kinetic energy in order to satisfy conservation of energy. On the other hand, let's consider a vortex-antivortex dipole. Again, in the non-dipolar limit, you have translation of the vortex-antivortex dipole along the binormal, and this happens at a velocity that's solely due to the separation between the two vortices. On the other hand, with the dipolar interaction, we'll consider two cases. One where the dipolar aligning field is parallel to the separation, that's in blue along the x-axis, or anti-parallel along y. Sorry, the other way around. Y is the vortex and anti-vortex are separated along y, and red is where the dipoles are parallel to the separation, and x is where they're orthogonal to the separation. So what you can see is as you increase the dipolar interaction strength, for the anti-parallel, for the orthogonal case, the velocities decrease as a function of epsilon dd monotonically. And on the other hand, for the parallel case, they increase. We attribute this to the same effect where, due to the interplay between the vortex-vortex dipolar energy and then the traditional kinetic energy of the dipole, traditional kinetic energy of the vortices, you can have different velocities.
During evolution, the vortices didn't separate or got closer to each other, which is parallel to each other.
They are parallel to each other, and of course, at the very beginning of the evolution, whatever the value of the dipolar interaction strength and whatever the polarization, they do get very slightly closer together, but I think this is just an effect of the numerics where there's a slight rearrangement of energy. But after that, you get this behavior where it's, there's no change in the separation. So it's just a change in the velocity. And now, while I have a few minutes left, I'll talk about vortex-vortex reconnections. So consider, okay. Okay. I'll finish it. Yeah. I'll have to skip the crow instability and this. Definitely. Something that happens in superfluids is where you have a vortex and an anti-vortex with Kelvin waves, you can have a growth of the Kelvin waves until you see reconnections. So this is the so-called crow instability. So I'll just very quickly play a video. They will reconnect in about 10 seconds, I think. Yeah, so the Kelvin waves increase in amplitude until you get reconnections and the formation of loops, and there's a loop cascade. So what we looked at is how this is affected by the dipole-dipole interaction. So we populated a vortex and an anti-vortex with the first 20 modes supported by the box, used the same noise profile regardless of what the dipole alignment is, and we looked at the reconnection times. So there's a strong dependence of the reconnection times on what the dipolar polarization is and also the interaction strength. What else? And you can see basically in the two cases at the bottom, X and Y and Z, the reconnections happen, X and Z, the reconnections happen at the same time for a particular choice of epsilon dd, but for Y, it's considerably suppressed. And recall that earlier there was a dependence of the velocity of the dipoles on the dipolar polarization. We see a similar thing happening over here where the dipoles have moved by a similar distance, but they've moved much less in this simulation over here. So we think that the suppression of reconnections in that particular case is due to the fact that the dipolar interaction has forced the vortices to move at a much slower rate. And I'll skip this last one. So I'll talk about the conclusions. We found that dipole-dipole interactions considerably alter the behavior of vortices, both in the ground states and also in their dynamics. So this raises a few questions. For instance, can you modify the Biot-Savart law to account for the dipole-dipole interaction? Also, does the vortex-vortex distance during the reconnection process still follow the t to the half scaling? What's the role of quantities such as curvature and torsion? And something that's definitely a theme of this workshop, can you create turbulence in dipolar BCs by having a time-dependent dipole polarization? Because we can clearly see that the vortex-vortex behavior dynamics is strongly affected by the dipolar interaction. Thank you.